This is cpe225, lecture 19. What we're going to look at today is some hardware considerations associated with RISC-V. So we've talked about many of these elements, either directly or indirectly, but now we're going to talk about them as pretty directly on this one. Let's go take a look at these. Okay, so anyway, RISC-V, as you know, it was defined by the instruction set. And so what it was a list of instructions, and it defined what those instructions had to do. And typically, it defined those using RTL, which is Register Transfer Language, which is kind of a high-level way of specifying what computers do. Okay, so the one requirement of the RISC-V hardware was to make the instructions work. And it didn't tell you anything about how to implement the hardware. You're just responsible for making it work. Okay, so programmers, I'm sorry, I think they just need to know, they just have a feel for how the instructions are implemented in the actual hardware. You don't need to know exactly how it works, but if you have just an inkling of how it works, it's going to make you a better programmer. And also, it's going to prepare you for cpe315 if you actually go on to take that. So what I did was took the hardware diagram that we actually implement in cpe233. I chopped out all the unneeded stuff into this, and essentially I chopped out the detail that was needed for hardware implementations. But what I left in was kind of the control and data connections, and so you could see how data flows through this thing. And so what I'm going to do is I'm going to describe kind of the top level, then describe the individual modules, and then along the way I'm going to describe some instructions and how they relate to those modules and how those modules use them. So this is the RISC-V computer high level. I chopped out all the stuff I don't think that fits in this diagram. Certainly you see a lot of control signals in this thing, but that have names. I just got rid of them. I just called them control. Okay, and so we'll be working with that. And I guess we're ready to crank out on this thing. And so first thing we're going to do is look at this top level module. This is how the outside world sees the RISC-V computer. And so what you see in this thing is you see a clock, number one. So this thing, of course, has a clock, and everything in this thing is synchronized to that clock edge, and the data transfers, et cetera, et cetera. We'll get more into that when we talk about the control unit over here. Another thing here, we got the interrupt, which is part of our real-time programming approach for this thing, and then we got the input data. So this is a computer that inputs data. This is, it could be a button press or something like that. This is data coming in from the outside world. Okay, so what we have in the output, essentially, this is a microcontroller that outputs data. There's the output data, and by God, it outputs that port ID also. Both the data and the port address are used by the level of hardware above this RISC-V microcontroller that you don't see here, beyond the scope of this class, but it's actually super important stuff. Okay, and that's the top level. And there's the top level information. And next we're going into the control unit. Okay, so the control unit is this thing over here. And the idea here is what this is going to do is decode the instructions, roughly speaking. So if you remember, the instructions are made up of opcodes and field codes. Field codes is kind of data that we're going to talk about later, but the opcodes describe what the instruction is. So this unit is going to read that and roughly output the right data. So this is kind of a status input, and it's going to output a bunch of control. This control, you could see it in various places in the circuit. It's essentially controlling the flow of data through the circuit, and it's really, however you put it, it's what makes it a computer on this thing. It does have a branch instruction input, and I'm going to say it's going to input status in there, If you remember the branch instructions, do some type of comparison. The result of that comparison is going to the control unit. The control unit's going to say, hey, you know, should I take this branch or not? Whether it takes the branch or not, it essentially sends data over to this mux over here. It chooses which data to input into this program counter. So the program counter, if you remember correctly, is either going to go to the next instruction, or it's going to support the branch or jump, and it's going to jump to somewhere else in the program. It does have an interrupt input, which is coming in from the outside world. Also, once that interrupt happens, what you're going to see is that the control unit goes into a special cycle. It sets everything up to handle that interrupt. And so, in general, this control unit is a finite state machine, and in hardware, finite state machines are little pieces of hardware that control other hardware. So this is essentially a controller circuit. It does have a clock signal here. I should say that. Here's your clock. I didn't really connect it to anything, but every time you see this triangle here, it indicates that this device is edge sensitive. So the things that happen in the circuit happen on a clock edge, and this is particular a rising clock edge in here. And let's see, the other notion of this control of this whole computer here is things have to happen, and they have to happen in order, but things like particularly this memory here has a control, some control inputs on it, and these memories act synchronously. So typically I have to figure out what the instruction is maybe, and then I see that it's some type of memory blah blah blah, and then I have to calculate an address, and then I have to give the address to the memory and then hit it with a control signal. So roughly what I'm saying is most of these instructions take multiple clock cycles to implement. Now this is something that's beyond the scope of the class. I mean, it would be comfortable to think that every instruction operates in one clock cycle, but it's simply not the case. So, and you'll see this later. The clock cycles are broken up into little periods such as fetch the instruction, decode, write, and read. All these things that kind of describe what's happening per clock cycle. But once again, this information's beyond what we need to know. And there's a control unit. Next thing we have is a program counter. So we've talked about this before. Then the program counter, the output of the program counter is this thing, and it forms the address of the instruction that is being implemented. That's kind of the general definition, but quite frankly, it's sometimes, depending on when you look at it, it's the address of the instruction being implemented. Sometimes it's the address of the next instruction. Like I said, it's kind of hardware dependent, and depending how the hardware is implemented on this thing. It is a 32-bit register, and the idea here is it supports the full 32-bit address space. Doesn't mean that there's 32 bits of physical memory, but it does have the ability to support all those addresses. So keep in mind this handles two types of instructions. That's normal instructions, which is just advancing the program counter by 4, right? It goes from one instruction to the next, stepping through the memory in a sequential manner, or it handles the jumps and branches. So the jumps and branches are the type of instruction that says, hey, go somewhere else to do something. And the idea here, it is under control. The control unit sends out a control signal, and it sends out the control signal to that mux. Also, it is a register, so typically I need to load that data into the program counter as well. So there's going to be a load control signal as well. There's the program counter. Next, we have the main memory. Okay, this is the main memory, and the idea, we call it the main memory because there's all sorts of memories in a real computer, such as secondary memory, which is something like a hard drive, and then we have other memories such as data caches and instruction caches. Once again, this is out of the scope of this class. That's something you're going to learn about in cpe225 if you take it. So essentially, the data caches support parallelism, which means you can essentially get more throughput per clock cycle in a computer like this. So the what you see here is this memory, I'm going to assume it handles both the instruction memory and data memory, so I need to give it an address. Oops, let's get this right. I need to give it an address of, well, here's the instruction address, but I also need to give it a data address when I'm dealing with data. And if I'm writing data to this memory, I also got to give it the data as well. Certainly, it's a typical memory. It works with control signals. To make the memory work, I need to tweak the control signals. The interesting thing about this memory, of course, is the output. And so the output on this thing is going to be the instruction word, which goes to different parts of the computer, which we'll talk about later. Particularly, part of that instruction, essentially the instructions are made up of opcodes and field codes. The opcodes go up to the control unit. The field codes come down to these other two units here, and we'll talk about that in a second also. Okay, so every instruction here, it's read from main memory. It's stored in memory. It's read from memory, but we have other instructions that are not essentially they're not instruction oriented. They're essentially the load and store instructions. So the load instructions are going to read data from memory and write it to the register file. Okay, the store type instructions are going to read data from the register file and store it in memory. So when I'm writing to memory, when I'm storing to memory, I need to give it data and an address. When I'm reading from memory, all I need to do is give it an address. Essentially, it's the address location in memory that I'm reading from. And I think that's it for memory. Next, we have the register file. This is the register file right here. And if you remember correctly, we have stuff like, I should have put it in here, add x10, x11, x12. Essentially, it's reading from data from two registers and writing to another register. And so what you're going to find here is this is actually, it is a piece of memory, and it's a special type of memory, which is referred to as a dual port RAM. And once you hear terms like dual port, blah, 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 what that means to you is it's a special RAM. It's special to us because it can read two independent addresses, which is these two things, and then it can write one address. Now these three addresses, there's 32 registers, so each of these address lines is going to be a field, which means field code in the instruction word itself, and you can see it coming right off the instruction on that thing. So it's going to read, worst case, it's going to read, be able to read two registers and write to a third register, and they can all be different registers in this thing. So when it's reading, it is it's going to take the registers at these addresses and produce them on these outputs, and it's going to be under some control signals that we didn't put down there. The interesting thing about this is those are essentially memory reads, but we have a choice of writing 4 different pieces of data to this register. So it can either be the result of a memory load. Remember, a memory load is going to come from memory and go into the reg file. It can also be a result of an ALU operation. So you can see this ALU operation come down here through this thing. It can also be associated with a jump instruction. If you remember, the jump instruction actually saves the address of the PC in a register, and you can see that connection right here. And lastly, it can be the input data. Input data goes, by design, it goes from the outside world into a register file. So those are the 4 pieces of data we can put into this thing. It's defaulted to 32 bits, which supports everything, although your I/O may not be 32 bits. So I guess, let's see, anything else on this writing to memory? Since it's going to take one of these registers and use it as a base address, but it's going to take the other register and write it to memory. And I'm just trying to remember which one it is here. It's Reg2. If you look at this thing, this data is coming over here, and that's what gets written to memory on a store operation. The address, it goes over to the ALU, calculates that address, and you can see that come over here for the address. It's the output of the ALU because it has to do an add instruction like, such as, for example, load word x10 for x20. Okay, so arbitrarily what we're doing is we're using the ALU to add the value in x20 to this immediate value of 4 to create the absolute address, and pretty much more on that later. Well, that's the register file, folks. Next thing of interest here is this immediate generator. Now, this is not too complicated. Now, the issue is that there are immediate values in this thing, and they represent field codes inside the instruction themselves. So those field codes they can range anywhere from 12 to 25 bits worth of information in any given instruction. And the idea here is I got to take those field codes, which are not 32 bits, and I need to convert it to 32 bits. Now, some of those field codes represent signed numbers, so I need to sign extend those numbers. Some of those field codes represent unsigned numbers, so I need to zero extend them. Okay, so keep in mind that there's also address data associated with branches and jumps, which, if you remember correctly, the jump data is stored as relative addresses, and it's stored as signed numbers. So essentially, that number is definitely sign extended. But what else you have to do is like a load instruction, load immediate x10 4, right? You've seen this a million times. Anyway, that 4 is essentially stored as a 12-bit value, and it needs to be extended to a 32-bit value before it actually gets added. And then, load immediate instruction is a pseudo instruction, and it actually is translated to an add type instruction via the assembler. But anyway, so all this module does is it takes values that are not 32 bits and it makes them into 32 bits without changing the value of that number. And it does so via sign extension and zero extension. The next module here is this absolute address generator. So once again, the big thing here is when I do a jump and a branch, where I need to jump and branch to is stored as a relative address. So the relative address is essentially a signed number because it could jump forward and backwards. It's typically it has different amount of bits in this thing. I think some are 12 and some are 20. I'd have to look at the spec. I can't remember now. But anyway, they need to be extended into 32-bit value. And so what's going to happen here is this module here is going to take all those values and kick out an absolute address. So for the branch instructions, it's going to take the immediate value and add it to the PC. You can see it there. It's going to be the same thing for a JAL instruction. It's going to take the immediate value and add the PC to it. But for the JALR, it doesn't use the PC. It's actually used the register value. And here's the register value coming down here. It's going to add that to the immediate value, and that's going to be the absolute address that the program counter is going to load. Now you can, I kind of lumped these together here. There's actually going to be 3 different instructions, one for the JAL, one for the JALR, one for the branch instruction, 3 different addresses. And whatever the control unit is going to send, it's going to know what instruction it is, and it's going to make the selection of which of these values to load into that program counter. And I think that's all I can think about saying about the absolute address generator. And then we got the arithmetic logic unit. Okay, so this is the arithmetic logic unit right here. Okay, so it does a lot of work on this thing. It does all the number crunching and I don't know, we'll say bit manipulations of this thing, and it has to handle like two types of instructions, roughly speaking. So it's going to be something like this, and then also has to have the add immediate x10, x11, 1, 2, 3, 4. Okay, so it has to add both of these. Sometimes it's going to take the immediate value. Sometimes it's going to take a register value. And what I'm going to do here is use these muxes to input the correct values into this ALU. Okay, and it once again, the control unit is going to decode the instruction. It's going to figure out what instruction it is and make the correct selections on these two muxes. Additionally, the control unit is going to decide which instruction, which operation to perform on this. And this is like add, subtract, shift, and all the logic operations and all that stuff like this. Once again, it's the control unit looks at it. It looks at the instruction, looks at the opcodes of the instruction, sends out the correct control signal to this ALU here. So the output of the ALU serves two purposes. Number one, it becomes the output address, and we'll talk about that in a second when we talk about I/O. But also, this result feeds back around over into the ALU. So when I do add operations like this X10 here is destination register. That result is stored in the destination register, whatever one's called out. And I'm trying to think of anything else in this one. Yeah, it does also, I forgot, it also does when I have a load or store type instruction, X10, 4, X20, it does this calculation also. So this is arbitrary. If we didn't use the ALU, we would have to put another adder in there, which is extra hardware, but this is a matter of reusing some of the functionality that we already have in here to do this calculation. Remember, this calculation we need to do to calculate the absolute address to we'll say, get that data from, since this is a load instruction. Last thing here is input and output, and I think it's not really a module, but we're just kind of pretending like it is a module. It usually appears like a box in any diagram, but we don't really have anything like that here. So an input operation would be something like a load operation. We'll just say 0x20. Okay, so this right here for an input operation is going to be the port ID. This can be an offset if you use it. This is the register that you're putting the data into. So the input data is coming from the outside world, and it's going into a register through that path right there. Okay, and the hardware is going to look at this absolute address and decide whether it's physical memory or not. If it's not physical memory, it's smart enough to do an input operation. If it is, if it's physical memory, it's smart enough to do a load operation. So once again, the hardware differentiates that for you. So what else here is that's an input. We got the output. Okay, so an output instruction would be something like a store word X10, 0x20. Same idea. This happens to be a destination register. This is actually, once again, since it's a store instruction, this is a source register. And the idea, it's going to take the data in this register, and here it goes right here. This is output data is coming out of this register, and it's going to toss it out at this address. Now it's going to, once again, it's going to calculate this address using the ALU. It's going to add whatever this constant is plus this base address, whatever values in that register. That's what it's going to output to the outside world right there. And I think that's it. All I can think of on this thing. I think it would be, like I said, this is the quick, dirty version. I'm hoping that you see the advantage of knowing that this hardware works and having just a general feel for what's happening on this thing. One of the most important ideas here is that this does have a clock on it, and it synchronizes the transfer of data through this thing. This right here is a clocked element. This has a clock, this has a clock, and this has a clock. Everything else doesn't have a clock, which means that data just flows through it. Data is the flow of data through these modules, the ones well, not this one, but the ones I circled here are synchronized to the clock signal. The instructions themselves, they don't necessarily operate in one clock cycle. It's actually kind of complicated to get them to operate in one clock cycle, like physically speaking, but you'll see that in what they do when they pipeline it, which is a topic in your cpe225 class, you can actually effectively get one instruction executed per clock cycle. But once again, that's beyond the scope of this class. And I think I'm gonna leave it at that. By all means, if you have questions, you could email them to me.